Okay, hey, welcome back. So this is a review for the first test in Calc 3. And basically I'll be taking questions straight from our homework problems. So I'm kind of giving you a question pool, 11.1, thinking problems, like one, basically all of them in there. Anything goes, 1 to 17. So over here in your homework, you see I'm talking about the actual, like, this is number 6, problem 6. So anything all the way up to, I guess, number 17. So yeah, so these refer to web-assigned problems, not technically problems in the book. So anyways, 11.1, 1 to 17, 11.2, pretty much all, or 1 to 13, 11.3, 1 to 12, 11.4, 1 to 4, and then 7 to 11. So I'm not going to do any torque, no torque problem. 11.5, I'm thinking 1 to 11, and then 14 to 18. So what that means is basically none of those problems where you need to figure out the angle between planes. No angle between planes. And no distance between point and line. Obviously, distance between point and a plane or distance between two planes is fair game. 11.6, 1 to 4, and then 6 to 13, 11.7, 5 to 13, and that's basically converting cylindrical equations to rectangular or vice versa. Okay, so I'm not going to be worried about the spherical, cylindrical, back and forth to rectangular or vice versa. Okie dokie. Okay, so what I want to do in this review is just kind of go through and do a couple problems in each section, maybe hit one that I thought you may have had trouble with, and serve as kind of a reminder as to, hey, I don't remember how to do that, or okay, I don't need to study that. Okay, so let's take a look here. Here's a basic problem. Find the and when you're studying, what you could do is kind of hit this practice another version, and that should not affect your grade. Okay, so we can even try this practice another version. So I need two vectors built from the given points. In this case, you always take the terminal point and subtract away the initial point. So 5 minus 3, 2, 6 minus 4, 2. And then with v, 3 minus 1, 2, 8 minus 6, 2. Those are clearly the same. Okay? Vectors are equivalent. Unless I did something silly. Equivalent. And you use this to check your answer. Make sure you're using the proper notation on my test. Make sure I can read what you're doing and you're not just throwing random symbols out into the ether. Vectors. 2. Whoops, I forgot to do. Yes, they are equivalent. Thank you. Okay, so you can practice and it won't affect your grade. Okay. Let's look at number 13. I don't think I really talked about this in my video, so I wanted to hit that now. It's important for later on because we'll be looking for these normal vectors and unit normal vectors and unit tangent vectors. Where are you, number 13? So number 13 here, they give you a function, f of x equals negative 3x squared plus 5 and a point. And they want a unit vector parallel to the graph at any given point. So that means basically find the derivative and use that to get a slope, and then that will be your vector. Okay, so f prime, it has to be a unit vector. F prime of x is negative 6x. At the point 1, 2, we have the slope negative 6. So our direction is going to be, if you think of negative 6 as rise over run, so the run is 1, the rise is negative 6, you're going down 6/1. And then I need a unit vector, so I'm going to have to find the magnitude of that thing. So that would be square root of 1 plus 36, which is square root 37. And then get the unit vector. So in the same direction as v, that would be 1 all over square root 37. And then negative 6 over square root 37. Okay, so that's part A. Part B, find the unit vector normal to the graph. That's fairly simple. All you have to do is take this vector u here and exchange the coordinates and negate one of them. Okay, so exchange the coordinates. So this will be 6 over square root 37 and 1 all over square root 37. And you make it negated accordingly. So for the graph, the pictures here, you know, we're after this well, that's not correct. It's this one we're after, I believe. Right. Where's the point? 1, 2. So here is a sketch of my graph at 1, 2. I'm like right here. So the part A would be this vector, and then we want this other vector, I guess, that either points out or points in. There's two possible normal vectors. Okay, from the picture, we want the one that points out. And if you look at that vector, its components, the horizontal component has to be positive, and the vertical component has to be positive. Okay, so we can determine the signs from the picture. I mean, literally there are, again, two solutions depending on which way you want your normal vector pointing. So you could have it pointing inside, you could have it pointing outside. So it's really up to you, but given that they give you the picture, you have to have this plus relationship. Obviously the one pointing in would be negative, negative. So the other possible solution would be negative 6 over root 37. In other words, I kept this component the same, but negated this one. Okay, so made it negative. That's what I mean by negate. Like abusing my vocabulary, but that's what I mean. Okay, so those are the two possible solutions. I probably won't make you sketch it on the test, but if I do give you a problem like this. There's some physics problems are fair game. I just wanted to hit this last one here. I wasn't sure if people were good with this one or not. It's probably a little bit too long for my test, but I just wanted to at least hit part A and kind of show you how it would work. So I'm dealing with this hanging object, and what I usually do is draw what they call a free body diagram. So I have there's tension on these two, so I'll represent those two strings with vectors, and then there's tension going downwards because of the weight. Okay, and then I kind of center my origin right here at the middle, and then I could describe the angles. So if this is 30 from opposite interior angles, this is also 30. And if this is 50, this is also 50. So this is CA, this is CB, I'll call this CM. And I want my vectors directed in the appropriate direction. And if I just let my angle be 50 degrees, it won't be directed correctly, and you may have some issues. So instead of using 50 degrees, what I'm going to use is 180 minus 50. Okay, so that will give me that angle, and I'll be able to describe this vector CA as some constant, I'll just say constant A times cosine of 180 minus 50 is 130, comma A sine of 130, and then CB, I'll say is some constant B times the cosine of 30, and then some constant B sine of 30. And then if you add in this, I'll just call it CM, so pretending these are all vectors, that vector would be 0, comma, negative, whatever the weight it is. So in this case, it was negative 1,000. Okay, Those vectors, because the thing is in equilibrium, the vectors should all add up to 0. Okay, so from there you can equate that. You can make an equation with the components. So the first components, the x components, will be a cosine 130 plus b cosine of 30 plus 0 equals 0. And then you could solve for a or b. B cosine 30 equals negative a. Let's solve for a instead, because that's what I did in my notes. B cosine of 30. Whoops, I just. A cosine of 130 equals negative b cosine of 30. And then, of course, a equals negative b cosine of 30 all over cosine of 130. Then the other equation is a sine of 130 plus b sine of 30 equals minus 1000 equals 0. Then you could substitute in for a, and get negative b cosine 30 sine of 130 all over cosine of 130 plus b sine of 30 equals 1000. And then you can solve for b, whatever the heck b is. So you would get b times negative cosine. Let's rewrite sine 130 over cosine 130 as tan of 130 plus sine of 30, and this is cosine of 30 in here, equals 1000. And then you can solve for b is negative. Let's just keep the negative in the bottom. 1000 all over sine 30 minus cosine 30 tan of 130. Okay, so you get this, whatever the heck this thing is, and it looks like it's 652.7, and then you substitute it in right here and get your A answer, which should be 879.4. Okay. You could do the same process for part B, but they don't give you the angles. You can always get the angles using like a tan inverse function. But if you want to, you can instead just use the vectors as they're kind of described. So the vector CB would be 24 comma, or rather 20 comma 24, and then times some constant. But at the end, you're going to have to go back and find the magnitude of that vector. The way that the A and B is set up right now, the A and the B are the tension that you're after, because the rest of it, the magnitude would just be 1. So you have to, but if you do it the other way, it becomes different. I don't know. If you're super interested in that problem, just let me know, and I will kind of write that out as well. But I think part A is good enough to just give you a flavor for how it would work. Okay. Okay. So that's I probably won't put that one, but 15 or 16, that's fair game. Let's look at 11.2. And 11.2, we were introduced to the idea of the distance formula and here in space, spheres, and just working basically with vectors in space. So let me cruise on over to those problems. Assignments. Yeah, so you see a bunch of these now we're in 3-dimension type problems. Let's look at problem number, number 6. So, and this, they can give you some pieces of information about the circle, and then you have to give the equation of the sphere, YZ plane. So basically, because it's tangent to the YZ plane, you kind of know then the radius must be 8. So that's just the distance from the center to the YZ plane. Okay, yeah, because if you look at the X, Y plane, you know that the center is at -8, 1, 2, 3, 4, 5, 6, 7, 8, 0. So the cross section of the sphere in the y-x plane would be this thing, and then you know it hits right here at 0, 0, 0. It has to hit right there. It's the only place it can hit. So the radius must just be this distance, 1, 2, 3, 4, 5, 6, 7, 8. So there it is. And from there, you have the equation of a sphere, which is x minus x sub 0, where the x sub 0 comes from the center. Right? This is x sub 0, y sub 0, z sub 0. So you get x minus negative 8 squared. So you have to have that formula memorized for a sphere. Y minus 0 squared plus z minus 0 squared equals r squared, which is 64. So that would be x plus 8 squared plus y squared plus z squared. That's 64. There's a midpoint formula in there. There's a distance formula in there. And then there's all this junk where you're dealing with vectors. Let's try one of those. Let's try number 9. Okay. Okay, so again, this is kind of, they give you an initial and terminal point, build your vector, and find the unit vector in the direction of the given vector. So 2, 0, 4, 1, 4. So v, just the difference, 0, negative 1, 4. I need the magnitude to get the unit vector. So that would be the square root of 0 plus 1, negative 1 squared is 1, plus 4 squared is 16, so we square root 16. So the unit vector multiplying by 1 over square root 16, 0, negative 1 over root 16, 17. I forgot how to add. And then comma 4 over square root 17. And that will be it. So those are pretty simple. Let's move into 11.3. So I believe 11.3 we're getting the dot product, our first type of multiplication, quote unquote. Dot product results in a scalar. And let's take a look. Geometrically, there are some relationships with the dot product. So cosine theta is u dot v all over the magnitude of u times the magnitude of v, and the relationships therein. Let's take a look at number 5. So we said the dot product is also a measure of the alignment of vectors. So we could tell if two vectors are orthogonal just by taking the dot product. In this problem, we want to know if they're orthogonal, parallel, or neither. So u is j plus 2k. If there's no I component, you just assume that's a 0. So it's really 0i plus 1j plus 2k, if you wish. Our vector v is 1i minus 4j minus 1k. And I could see that if they were parallel, the components would be multiples of each other, right? I'd just be able to multiply something times this component, this I component, and it would equal this I component, 0. So the only way it could work would be if the multiple, if it was 0, right? Because v is parallel to u, if and only if, I believe, I'll just say, if that's true, then v equals a constant multiple of u. Okay, in this case, it's clearly not true, so it's not parallel. Are they orthogonal? You can take a look at the dot product. So 0 times 1 is 0, plus 1 times negative 4 is negative 4, plus negative 1 times 2 is negative 2, so that's negative 6, so it's not orthogonal. So it must be neither. We could find the angle between the two by just taking cosine inverse of the dot product, which is negative 6 all over the magnitudes. So the magnitude of the first one is root 5, the magnitude of the second one, 1 plus 16 plus 1 is root 18. And if you were ambitious enough to put that into your calculator, you get 129.2 degrees. So definitely neither. Yeah. What else do we have? We had projections in this section. So the projection formula, the projection of u onto v would be u dot v all over the magnitude of v squared. That would be a scalar times this vector v. Okay, so let's find a projection problem. So we had some physics problems. What about number 7? Just simply put, right, so number 7, U is 7, 5, V is 2, 6. Okay, we want the projection and then the vector component orthogonal. So remember, they would call this W1, and then note that W1 plus W2 would equal U. So W2, the orthogonal projection, would be U minus W1, okay, because of the relationship of the vectors. So you would have the projection vector, W1 would be like right here, and then W1 plus W2 would equal this U vector. Okay. This is U, and we're projecting onto V. Okay, so anyways, yeah, let's find the projection of U onto V. So I'll go back to black. Projection of U onto V is, what do we got? 14 plus 30 all over the square root of 49 plus 25 times the square root of 4 plus 36 times the vector 2, 6. Okay, so that would be 44 all over some big mess, right? Jeez. Oh, sorry, I was still thinking in terms of something else. So this would be V, just the magnitude of V. So it's 4 plus 36, square root of 4 plus 36 squared. That's just going to be 4 plus 36, 40, right? And then so you get 44 over 40 times 2, 6. Simplify, that's 11 over 10. It's 2, 6. Simplify even more. So that should be 11 fifths, comma 33 fifths. Okay, so that would be your W1, and then for W2, you're taking U, which is 7, 5, and then subtracting away W1, which is 11, 5, 33, 5, and so we get 35 fifths, comma 25 fifths, minus 11 fifths, comma 33 fifths, equals, oh boy, 24 fifths and negative 8 fifths. And that's the orthogonal guy. Okay, let's look at one work problem. So remember, work is equal to the dot product of the force and the distance traveled. But we can rewrite that in terms of the angle between the vectors as the magnitude of the force times the magnitude of the distance times cosine theta. Okay, so let's look at one of those work problems, probably number 11 here. So object is pulled 14 feet, so we kind of have the magnitude of the PQ thing, which is the distance. The magnitude of the force is 67 pounds. So magnitude of force is 67. The angle theta is 60 degrees. So this one is just, you're using this version of the formula. So usually it's just come down to, are you going to use the dot product, or are you going to use this cosine theta version? So anyways, the work then, and the work is not a vector, it's a scalar. The work is equal to 14 times 67 times cosine of 60. And if you put that in your calculator, you should get 469 foot-pounds. Okay. Make sure you have the appropriate units going on. So this is in feet, the other one. It doesn't seem like they're trying to trick you in any of the problems here. Okay, let's go on to 11.4. So 11.4 gives us our second type of multiplication for vectors, the cross product, which ends in a vector, the vector which is orthogonal to the original vectors. Okay, so the typical problem in 11.4 would be something like number 3. So just verifying, I'll just be kind of first verifying that you know how to do a dot product. So U is given as 7i plus 7j. V is given as negative 7i plus j plus 7k. Okay, so find U cross V. So the I, J, K. 7, 7, 0, negative 7, 1, 7. And then you cover up the first one, so you get 49 minus 0. It's 49. The second guy, 49 minus 0 again. So it'll just be 49. And then the third guy, remember the second component's always the negative of whatever you get for the determinant. And the third guy, 7 minus negative 49. Whoops, I mean 49. Yeah, 7 minus negative 49. 7 minus negative 49. Okay, so we're getting 49, comma, negative 49, comma, 7 plus 49 is 56. That's our cross product. And then you see whenever you take the dot product with the original vectors, those are orthogonal. So I may ask you to do that on the test as well. All right, one important thing that comes up later, so I'm not going to put the torque problems on, but one important thing is that you can use the cross product to find the area of a parallelogram determined by these vectors. Okay, so problems like number 4 become important later, but honestly, by the time it becomes important, you've probably forgotten it. But anyways, I hope you won't forget to find the area of a parallelogram kind of traced out by the vectors. So our U vector in this case, ijk, the V vector, 0i, 1j, 1k. Okay, so the area of the parallelogram of these given vectors will be the magnitude of the cross product. So first I need the cross product. One, 1, 1, 0, I, 1, 1, 1. Okay, so this will be 1 minus 1, and then negative 1 minus 0, and then 1 minus 0 again. So this will be 0, negative 1, 1. And then the magnitude, which would give the area, will be the square root of 0 squared plus negative 1 squared is 1, plus 1 squared is 1, square root 2 is the area. Okay, 11.5 throws us into working with lines, equations of lines, and equations of planes, and then distances, right? So 11.5. First, let's just work with finding the equation of a line given some information. Right, so we can give you all kinds of weird information. You have to figure out the answer. Let's try number 3 here. So they give us 2 points. And we have to figure out our answer. Okay, so I need basically a direction, and the direction is kind of like the slope, and then a beginning point. So to find kind of the quote-unquote slope, I'll call that V. I'm taking the difference of these points, right? So in this case, I'll have negative 2/3 minus 5, or 15/3. Then I have 2/3 minus negative 3, which is negative 9/3. And then I have 1 minus negative 2, so 1 plus 2 is 3. This will equal negative 17/3, 11/3, and then 3. Because this is only direction, we only need the direction information from this vector. You can resize it by multiplying by 3. So 3v will give us something easier to stomach. And then the equation for a line, it's just a set of all points x such that when you make a vector, it's parallel to this given vector, right? So making a vector xyz, a vector with the point xyz and 5, -3, -2, that will be x minus 5, y minus -3 or y plus 3, and then z minus z plus 2. That vector has to be parallel, in other words, a constant multiple of this directional vector. And so I can equate the components here. X minus 5 is -17t. So x is -17t plus 5. Y plus 3 is 11t. So y equals 11t minus 3. And then z plus 2 equals 9t. So z is 9t minus 2. Then you need the symmetric form. So working with these guys, you can kind of reach off that, and you get t equals x minus 5 over -17. T equals y plus 3 all over 11. And then t equals z plus 2 all over 9. Okay. So that would be the first, the parametric equations here, and then the symmetric equations here. Okay. Okay, so there's that junk. Finding equations of a plane. So let's try. I guess let's try 8. The point on the plane is 9, 3, 3, and it's perpendicular to this thing. So let's say t equals x minus 1 over 6. So x minus 1 equals 6t, and x is 6t plus 1. So what we're doing is finding the directional vector. It's perpendicular, so that may give us more issues, right? So if we want find an equation of a plane that passes through the point and is perpendicular to the given line. Well, that's pretty easy, because then the directional vector for the line will give the normal vector of our plane, right? So the normal vector, the first component will just be 6. And then the second component, y plus 3 equals t. So y equals t minus 3. So the second component is 1. And then z plus 9 equals -9t. So the third component is -9. And then the equation of the plane is basically the dot product of all vectors created by taking a point x, y, z, and so if you took x minus 9, y minus 3, and z minus 3, and you dot product it with this normal vector, it would equal 0, right? That would produce the equation. So the actual equation is that dot product. So 6 times x minus 9 plus 1 times y minus 3 minus 9 times z minus 3. And on my test, you can leave it like that if you want. You can get it into the other form, right? But this answer is fine for me. What else did they have in this section? They had distances between planes and graphing planes, but distances. So here we have the distance between a point and a plane, number 18. And basically that comes down to projection. So if you have a point up here, Q, and then you have a point here in the plane, P, you have a normal vector here given from the equation of the plane. So for us, the normal vector in this problem, number 18, is 1, -1, 2. We need to form this PQ vector. So I need a point from the plane. The plane is given by x minus y plus 2z equals 2. I have one point, which is 5, 6, 3. That's the Q point. I need a P point in the plane. So you could substitute in, right? 0, 0, and then you would have 2z equals 2, so z would equal 1. Okay, so you can make that your P and get a PQ vector. And PQ would be 5, 6, 2. And then the distance is the magnitude of the projection of PQ onto the normal vector, right? So that would just be the kind of scalar that's out in front of that the unit normal vector in this case. So that would be the absolute value of n dot PQ all over the magnitude of n. And so in this case, that would equal 5 minus 6 plus 2 all over the square root of 1 plus 1 plus 4. And so that would be negative 1 plus 2 is 1 all over the square root of 6. And then you can put that in your calculator. Is that right? I don't think that's right. Let me check. Calculator. Seems like it should be 2. Divided by 6 square root 2.44. Really? That's not right. It's 5, 6, 3. It's the original. Like, jeez. I see it. My dot product's wrong. It's right here. 2 times 2 is 4. All right, so that should probably fix it. That's 4 then. No, that's 3. Ugh, really? Let's see if that's right. Seems like I just went in the wrong direction. 3 divided by 6 square root of. Oops, I hate this calculator. 6. Whoops, nope. It's clear. 3 divided by 6 square root of. And it's still freaking wrong. 9, 6, 7, 8, 9. 4, 1 plus 1 is 4, 4, 5, 6. I didn't see what I did wrong. 3 divided by square root of 6. And I didn't change anything. Oh, I had it right. I just forgot to push the stupid button again. I hate this calculator on the computer. I never use it. Yeah, that's the right answer. Okay, anyways, so be able to find distances between points and planes. 11.6 was on quadrics. 1.6er. So what you should be doing in these problems is identifying the cross sections and then making a conclusion about the object that you're dealing with. So let's look at number 2. I won't be giving you the pictures, but I will give you the names of all the different quadrics. So you don't have to memorize the names, you just have to pick which is the right one. So I should see, excuse me, your cross sections, so x, y, and then a little picture for each. xy is 15x squared minus 4y squared equals negative 4. Multiply by a negative, so it's 4y squared minus 15x squared equals positive 4. And in the xy plane, that would give you kind of a parabola type deal where the arms are on the y-axis. A hyperbola, not parabola, excuse me. YZ, so all of a sudden I'm French. Okay, so YZ is negative 4y squared plus 15z squared equals negative 4. So multiplying by negative 4y squared minus 15z squared is positive 4. Again, that will be one of your hyperbolas, so YZ. This time with the hyperbola on the y-axis. And then xz, 15x squared plus 15z squared equals negative 4. That's the one where there's nothing in there, so automatically that tells you it's hyperboloid of 2 sheets. Remove 2 sheets. And that would be your answer. Okay, so those 3 things plus your conclusion. So expect some of those. Right, so that's 11.6. Last section was 11.7. 11.7. And that was converting from spherical and converting from cylindrical. I'll be focusing mainly on cylindrical equations, converting back and forth. So 11.7 from rectangular to cylindrical and vice versa. So get problem 7. They give you y equals x squared and rectangular, and they want you to convert over to cylindrical. So you have to have all your little formulas memorized. Y equals r sine theta. X equals r cosine theta. What are the other ones? X squared plus y squared equals r squared. Z, just plain as z. And tan of theta equals y over x. So here I can replace x squared and y with the r sine theta, r cosine theta. So y is r sine theta. Over here, r squared cosine squared theta. Ideally, you want r equals something. So here I'm going to divide both sides by r. And I get r cosine squared theta equals sine theta. And that usually is no big deal because in the end, your answer will include that point r equals 0. If you just let theta equal 0, you'll get that. Anyways, let's divide both sides by cosine squared. So you'll get sine theta times secant squared theta. Or if you'd rather, I think there was another answer, tan times secant. There's another answer there as well. So there's more than one answer. But when, try to get it r equals, unless there's like no way. For example, number 12. We have r equals 4 sine theta. Ideally, you would get y equals something, right? But here you're not going to be able to because this is a circle. So again, this time we're going, well, not again, but this time we're going from cylindrical to rectangular. I note that y is equal to r sine theta. So I could rewrite y as 4 sine squared theta, and that helps because I'm going to use this equation, the x squared plus y squared equals r squared, to kind of settle what's going on here. R squared on the right-hand side is going to be 16 sine squared theta, which looks an awful lot like this, right? So what you do is just factor the 16 into 4 times 4. And then this thing right here becomes your y. So you've eliminated your y term. And then we could rewrite it by completing the square. And you see it's a cylinder. It's actually a circle, but in 3 dimensions, it's a cylinder, right? So y squared minus 4y. I'm going to complete the square on this. 0 plus, then you have to add it to the other side. So negative 4 over 2 is negative 2. Negative 2 squared is 4. I have to add that to both sides. Factor the second term, so you get y minus 2 squared equals 4. And so in the xy plane, if I were to ask you to graph that, you would have 1, 2, 3, 4. You have a center right here, and it would go like this in the xy plane. And the xyz plane, which I won't ask you to graph because I don't think anybody in here is an art major. If you are, that's cool. Yeah, definitely. But I mean, if it looks nice enough, I'll give you a bonus point, But yeah, it should be. It has to look nice, though. I'm not going to give bonus points for something I could do on my own. 2, 3, 4. So there would be kind of our location, and then you could just take that thing and kind of draw it up the bar, and then there it is. Sort of. If we could do better than that, I'll give you a +1. Anyways, if I even put that on the test. So pretty much, anything from that question pool I gave you is fair game. So, you know, be aware of, there's a lot. I think I might have said that I was going to give you a formula sheet, but I don't think I will. You should have these the formulas I mentioned kind of memorized. There's not a lot of them. And you should be good for the test. Okay, there's no video quiz in the review videos. Okay, I think that'll do it, and we will see you later. Thank you for watching.